So in this video we are going to talk about preparing our training data set using utilities from Scikit-learn, and we will also talk about the transformer API, which is related to the estimator API that we talked about in the previous video. So the estimator API was for supervised learning models such as classifiers or regression analysis models. And the transformer API is more for data transformations, but it's relatively similar, and we will also see how that looks like later in this video. But before we talk more about it, let me briefly highlight the issues with random subsampling. With random subsampling here, I mean dividing a dataset into two subsets. So consider the example where I have 150 iris flowers and I'm dividing it into a training set of 100 flowers and a test set of 50 flowers. So here each histogram is showing a frequency distribution for the sepal lengths. However, what kind of feature it is doesn't really matter. I'm here more curious or interested in looking at the class label distributions. So you can see there are three colors. So the colors correspond to iris setosa, virginica, and versicolor flowers. And you can see when I randomly divide it up, the distribution changes. You can see that, for example, this here is relatively similar to here. However, the distribution here in the test set changes. So I would argue that we have now more setosa flowers in the training set compared to other classes, rather than in the test set where we have fewer setosa flowers compared to the other classes. So that is maybe a little bit confusing what I just said. So what I mean is, here in the data set we have 33% distribution of all the flower classes. So there are 50 flowers from each class, so there's a 33% proportion here for each flower class to be represented in the data set. Now when we split it, what happens is in the training set we may have now more than 30% setosa flowers in the training set compared to the other ones. So let's say it's something like 40, 20, 20, let's say, sorry, 30 now. So it's a little bit exaggerated, of course, but just to bring the point home here, the distribution changes if we randomly subsample and have a small data set, just to random effects. So it's a high chance that we skew the distribution if we have a small data set and randomly divide it. Now, so for example, if we have now more than 33% setosa flowers in our training set, we will have less than 33% setosa flowers in our test set. So the bias will be in the opposite direction because we only have a fixed number of setosa flowers, and if we proportionally assign more setosa flowers in the training set, we will have fewer for the test set. So here the distribution may be something like 20% now, and 40% and 40%. Of course, again, this is exaggerated. However, if we randomly subsample, what can happen is that we skew the class label distributions. And if we think of our whole data set as the population, then we introduce some bias here because one class will be, let's say, underrepresented or overrepresented in the training set, and the opposite way, it will be then underrepresented in the test set. So we have two types of issues here. First, we have a misrepresentation in the training set, and then we have another misrepresentation depending on the training set misrepresentation in the test set. So if we work with a sufficiently large data set, this is usually less of an issue, this skewing of the distributions. However, I think it's always a good idea to do something called stratified splitting. So stratified splitting means splitting by maintaining the class distribution or proportions in the subsets. So how we can do that in Scikit-learn is as follows. So here we are using the train test split function from the model selection submodule in Scikit-learn. And what this train test split function does, it's splitting a dataset into two subsets. So here my dataset is X, this is the features, the one, let's say 150 flowers, well, the features corresponding to the 150 flowers, and then my 150 labels. Say, let's call them instances, 150 features, corresponding to the flower instances, and 150 corresponding labels, and then we will split that into 20% as a test dataset, and then the remainder will be a temporary dataset. So what we will do here is we will define xtemp and xtest. So if the test set size is 20%, then we will have the 150 divided into 30 test cases, and the remainder, the 120, will be for, let's say, the temporary array. I will show you in a moment why we do the temporary array. Some other things to observe here: we are shuffling the dataset before we split that. That is useful because you know that in Iris the class labels are sorted. So you have first the 50 setosa, then the 50 versicolor, and then the 50 virginica flowers. If you don't shuffle, then the setosa flowers will all be in one dataset, for example. So we shuffle to have a shuffled dataset, and then we also set the random state for the shuffling, so we can reproduce these results later if we need to. And here, via the stratify parameter, we define the stratification. So here, for stratify, we actually provide the labels that we want to use for this stratification. And then, as a result, you can see here, based on the bin count output, which gives you the counts for the 0, 1, and 2 values, where 0 means setosa, 1 is versicolor, 2 is virginica, so the class labels. So this is the number of setosa flowers, the number of versicolor flowers in the second index. And the third index, index 2, corresponds to virginica. So you can see here that the distribution from the original data set, which was 50-50-50 flowers, is maintained. So we have a 33% proportion of each class in our new temp dataset. And if you would check y-test, you would find the same thing, that there's a 33% chance of each flower in the test set. Now we are going to repeat this one more time, because we are now dividing the temporary one, the 120 ones, into a training set and a validation set. So that is why I do two splits here. First, we are creating the test set. So we use a different color. We have the test set first, and then in the second one, we are creating the actual training set and the actual validation set that we will be using for model tuning. So we usually use a validation set for model tuning, and then the test set only for the final evaluation. But we will talk more about that in the future when we talk about model evaluation in more detail. So as a result, now here I'm using now ytemp, the class labels here again, for stratification, and then I will get 96 training examples. And if I have 96 training examples, 120 minus the 96, this would be 24. So I have 24 in my validation set, so 24 validation instances. And here, this is just illustrating the slide that we can do the stratified split using a train test split function and specifying the stratify argument. The next topic is data normalization. In particular, here we are talking about min-max scaling. So min-max scaling is a way of scaling a feature such that all the values will be within the range 0 to 1. So consider the case of the sepal length. So here x represents one feature. So x could be, for example, the sepal length feature in the iris dataset. And what we are doing is we are normalizing the sepal length such that it falls within the range 0 and 1. So we take the current observation of a training example. So I is the index over the training examples, and then we subtract the feature minimum value. So it's the smallest sepal length, for example, in our data set. And then we also here use the maximum feature value. So it's the largest feature value in our dataset. So we essentially, for each value in the feature column in our training set, we subtract the x min, the minimum feature value, and then divide by x max minus x min, and then we get the normalized feature value. So here's a simple example of how that looks like in practice. So imagine our original feature values are the values between 0 and 5. So let's say this is our feature column here. So what we do is we subtract the minimum value and divide by the maximum minus the minimum value. And then you will see afterwards the feature column will be in the range 0 to 1. So that is one way of normalizing. Yeah, another common data normalization approach is standardization. You probably have seen something like that in the other statistics classes you took before. So here, this looks kind of like the z-score computation, right? When we have a normal distribution and we want to convert from a normal distribution into a standard normal distribution. So that's the same concept here. We have a feature value and we subtract the feature mean and then divide by the standard deviation of the feature. And afterwards, so after that, the distribution, the mean of this feature column will be 0, so we have 0 mean, and the variance will be 1, so we have unit variance after standardization, and consequently the standard deviation will also be 1. Note that, however, these are only the properties of that feature, so the parameters of a normal distribution or standard normal distribution. But if the feature doesn't have or doesn't follow a normal distribution, it will also not have a normal distribution afterwards. It's just one way of affecting the mean, so it's centering at mean 0 and then scaling such that the standard deviation or variance is 1. However, if the if the distribution of the feature is not normal, then after standardization it will also not be normal. It's not important whether we have a standard normal distribution or normal distribution for the feature. Here, for most algorithms, the point is more about having 0 mean and standard deviation of 1. Yeah, so the rationale behind standardization is that 0 mean and unit variance are properties that help certain optimization algorithms, such as stochastic gradient descent. However, we will not be discussing stochastic gradient descent in this class. It's a thing I cover in 453. But in general, standardization is much more popular, for example, than min-max scaling. So in machine learning, most people use standardization rather than min-max scaling, and it's for these applications, it's fine to do either way, either or. So if we have a k-nearest neighbor algorithm, doesn't make a big difference whether we normalize all the features or standardize all the features. What's more important is that the features are all on the same scale if we use distance metrics such as Euclidean distance. And also in the next lecture, we will be talking about decision trees, and decision trees don't need any feature scaling at all. In essence, they will be immune to feature scaling. So standardization, though, is still a useful and important concept in other machine learning algorithms. So it's usually not a bad idea to just do it. So here's how standardization would look like in practice. Again, I have my toy feature column, the 0, 1, 2, 3, 4, 5 as possible feature values, and then I'm subtracting the feature mean and divide by the standard deviation. So as a consequence, I will get a new feature that is centered at 0 with a unit variance. Yeah, as you may recall from previous classes, the sample standard deviation has the n-1 in the denominator. That's the Bessel's correction term to make this an unbiased estimate of the population standard deviation. So in that case, that's the difference between the population and the sample standard deviation. Now, if you wanted to get a population standard deviation via pandas, you would have to replace this by delta degrees of freedom equals 0. Or if you wanted to get the sample standard deviation via NumPy, you would add delta degrees of freedom 1 here. That's basically the -1 here in the std function. In machine learning, by the way, it doesn't really matter whether you use the standard deviation corresponding to the sample standard deviation or the population. In machine learning, all that matters is that the feature is centered and has approximately unit variance. So whether you use the sample or population variance or standard deviation doesn't really matter at all. So you can use either or. Personally, I just use the population standard deviation because there's no advantage of using the sample standard deviation when we standardize the variables. So yeah, because I personally usually use NumPy when I work in machine learning, I would just use the population standard deviation because it's just easier to type than just putting the DDOF equals 1 here. And in practice, it does not really matter whether we compute a standard deviation for the sample or the population in machine learning when we standardize the features. What's more important though than talking about sample and population standard deviation is that we use the parameters of the training set when scaling the validation and test sets. So we use the training parameters for that. So for example, when you standardize features, you would get the mean and the standard deviation from the training set, from xtrain, right? So you get the feature mean and the feature standard deviation from the training set. And then you use that to standardize the training set here, right? And note that we also use the same mu and sigma, the same mean and standard deviation for scaling the validation set and also for scaling the test set. We do not recompute the mean or standard deviation from the validation and test set. So why is that? The intuition behind it is basically that the validation and test sets are unseen data sets. So at the point when you do the model training, you only know the training set, you don't know the validation and the test set. So if you would use the parameters or the validation and test set to scale these two sets, you would in a way have too much information. You would kind of cheat or leak information. I know it may seem a little bit unintuitive. However, I try to make a very simple example in the next couple of slides to illustrate why we reuse the training set parameters and a potential pitfall that can happen if we don't do that. So consider the simple case where we are given 3 training examples. These 3 training examples. And then we have some measurements for these training examples, like 10 centimeters, 20 and 30 centimeters. And the first 2 training examples belong to class 2. And the last training example, the third one, belongs to class 1. Now, if we would compute the mean of that data set, it would be 20. And the standard deviation would be 8.2 centimeters. So this is just our training data set, how it looks like. Very simple. So again, here's the training set from the previous slide as a reference. And then let's now standardize the training set. So to standardize the first training example, we would have 10 minus 20 centimeters divided by the standard deviation, which is 8.2, right? So this one would be our first one, which is minus 1.21. It's from here, right? And then I repeat the same thing for example 2 and example 3. So what I get as the new feature values is 0 here and 1.21 here. Of course, this does not affect the class labels at all. It shouldn't. It's just scaling the features, so the class labels are just as the class labels as before. Now this one again is from the previous slide, just for reference. Now assume we have a classification rule that is saying if z, where z equals the standardized feature, so let's call it standardized feature, I just call that z-score here. So if our standardized feature is smaller or equal to 0.6, we classify it as class 2, and otherwise we classify it as class 1. Now let's apply the rule. So if we take this rule here and check train example 1, then this one would be correctly classified, right? Because this one is smaller than 0.6. So we assign class 2, just like here. Then for the second one, 0 is also smaller than 0.6, so we also assign class 2. Now, the other case where z is greater than 0.6, that is what we have here. 1.21 is greater than 0.6, so we assign class 1 here. So this is our classification rule that we learned from the training set. We just assume we have some classifier that does this type of classification. Now assume I have a new data set. So I am giving new examples, and let's say this is our test set. Now we have a test set and we have the values 5, 6, 7 in the data set. So what would the prediction be? Before we do the prediction, we have to also standardize, right? Because our classifier was trained on a standardized training set, so we also have to standardize any future case. Now let's standardize the test set. However, we do the wrong way first, and the wrong way is using the mean from this new data set and the standard deviation from this new data set. So we estimate the new mean and standard deviation, and what happens is if we do that for these 3 cases, we will get again the values minus 1.21, 0, and 1.21. And then if we would use these, so if this is the standardized version of this one, if we do that, and then if we use our classification rule, we would get exactly the same as for our training set before. However, note that now in this new data set, the values are very different than the values before. So this doesn't look right? So it's really not a good idea to use the new data set, mean and standard deviation, for standardizing the new data set. What would be better is to use the training set parameters. So if we use the training set parameters, these ones here, what we get for the standardized ones are these values, and they make much more sense, because if you look at these here, they are values that are much smaller than these ones, right? So the values are way smaller than these values, so it's kind of intuitive that all the values, the standardized z-scores, are lower than this case, because this one here was the lowest value in my training set, right? 10 centimeters, and all of these are actually smaller than the 10. So, and consequently, the z-scores should be smaller than my minus 1.21, right? So if I would actually then use these values, I will get these smaller values. And this one is really not a good idea. So here, hopefully this example illustrates why re-estimating the mean and standard deviation for each data set when we do the prediction is not a good idea, and we in fact should use the training set parameters. Yeah, talking about normalization like min-max scaling and standardization brings us to the next topic, scikit-learn transformers, or in particular the scikit-learn transformer API. So this transformer API, or the transformer, the term here, is not to be confused with the transformers in deep learning, which are a type of neural network architecture based on the attention mechanism. So here we are talking about a transformer API, and transformer is more like for technique for transforming your data, such as like min-max scaling or standardization. So Scikit-learn has an API for all kinds of different transformers, such as standardization and min-max scaling transformers, which I will show you in the next slide. So here I'm just outlining the general concept behind transformer types in Scikit-learn. So similar to the estimators, what we have is a fit method. So we have a training data set typically, and then we call fit on this training data set here. And then we get a model, or you can also think of it as an object, a transformer object. And then using this model, we can transform the training data to get transformed training data. So in that way you can, if we talk about a normalization procedure, we can think of it as a normalizer, some object that normalizes the training set, and then transformed is basically normalized, like standardized or min-max scaled and so forth. And so after doing that for the training set, so after fitting the transformer object or model, then we can also use it on the test set or on any new data set. So we have a new data set here, and then we would call transform, similar to the training set, but note that what's important here is that we only call fit on the training set. We don't call fit again on the test data and so forth. Now here's how that would look like in practice using the standard scaler. So the standard scaler is for standardization. So recall we previously have done the standardization manually, where I did something like this, where I had, let's say for one feature column, I just computed the mean using NumPy and the standard deviation like so. And if we would have a design matrix with basically a matrix and training examples times m features, so like multiple features, we can then just put the axis in there, right? So we would say axis should be 0 because we compute the column means. And the same way here. So that would work for design matrices. Then after that, after we obtain these parameters, we can standardize the training set. So let's say xtrain st or something like that for standardized. We would call, or we would use the xtrain dataset minus mu divided by the standard deviation. Oops, it's jumping back and forth here, by the standard deviation. And then we can do the same thing for the test set. So we would have test st equals x test minus the same mu divided by the standard deviation. So instead of doing that by hand, like I just showed you, we can also use this standard scaler transformer. That's like what Scikit-learn refers to as a transformer, because it has like the transformer API. And then we can achieve the same thing by first initializing a new scalar object or transformer object. So I call that scalar because it's a standard scalar for standardization. Then I fit the standard scalar, and really what happens here, we use a different color, what happens in this step is essentially inferring the mean and the standard deviation from the training set, from the data set provided here to the fit method. So the scalar will then have a mean and standard deviation from the training set that it can then use to transform or standardize the training set. So then in the next step, like I've outlined above, it's equivalent to what I have here in red. This step would be scaling or standardizing the training set. And then if we have a new data set, like the test data set or validation data set, we can then also scale that one. But note that we are not calling fit again. So here the fit method is only called on the training set. And that is similar to not inferring the mean and standard deviation from the test set, but using the parameters from the training set. Yeah, one burning question now might be, why are we not sticking to this approach for standardization? Why do we need to use the Scikit-learn transformer API? Why do we have to use the standard scaler? Because it doesn't seem to be too much work to do it ourselves, right? So in the case of standardization, I agree it's a very simple procedure, so we can do it by hand. We don't need really a separate class from Scikit-learn from that. There are some more sophisticated transformation techniques that we will cover later on. Some are related to feature selection and feature dimensionality reduction, as feature extraction and stuff like that. That is more complicated to implement, and there the transformer API will become more handy. However, also the standard scaler is a very useful thing to have, as we will see later in the next video when we talk about Scikit-learn pipelines, because the standard scaler allows us to use a Scikit-learn pipeline where we can chain together a bunch of things to be executed on a given data set. So in the next video it becomes also hopefully a little bit more clear why it's useful to use the standard scaler instead of doing it ourselves. Okay, but to move forward now, in the previous slides I spent a lot of time explaining how we can deal with continuous feature columns like standardizing features. Now let's talk about how we deal with categorical data. For that I have a very simple toy data set here, which consists of 3 training instances and 4 columns. It's a very small data set. It's just like for illustration purposes here. So we have 3 feature columns and 1 label column. First, note that we have 2 categorical columns here. So these 2 are categorical. And this one here is a continuous one like before. Now let's talk about the size here first. So note that color and size are 2 different types of categorical variables. I will explain to you in a few moments how they are different. Now let's just start with the size, and you can think of it as something like, I don't know, t-shirt size. And if you have t-shirt sizes, these letters really just represent an order where you can say a t-shirt of size L is bigger than a t-shirt of size M, right? And similarly, a t-shirt of size XXL, or just XXL, is bigger than a t-shirt of size L, right? So there's an order here. So we have M smaller than L, smaller than XXL, and so forth. So this is a so-called ordinal variable. So how can we deal with that ordinal variable? The problem with ordinal variables is that we can't just have an algorithm guessing what that means, what M means, what L means, and stuff like that, because it can be just an arbitrary letter, right? So it could be a license plate number or a letter or something like that. So how can the computer know that this is indeed an ordinal variable? There's actually no way. This is where we as a human have to provide some guidance to the computer. So I would say the best way for dealing with such ordinal data is really just doing our map approach using the pandas data frame. So where we define our mapping dictionary and then transform this feature. So in this case I was assigning the number 2 to M. There might be, for example, an S, it could be a 1 or something like that. I was assigning a 3 to the L and a 5 to the XXL. Maybe there's an XL with size 4, but this is really arbitrary. I could also choose numbers like 2, 5 and 13 or something like that. Because maybe the size or the difference between M and L is less than the difference between L and XL, or of course also L and XXL. So what I mean is the interval between those two, and if we have, let's say, do ML, XL, the interval between those two doesn't have to be like the interval between L and XL, could be a different size. So that is something that really depends on the application or on the data set. So there's no way really that there can be an automatic way for assigning these numbers, and that is actually then where a domain expert who knows about the data would come in handy. Next, let's take a look at the class labels, which are another type of categorical data, namely nominal data. So class labels, as you know, don't have any order. Even if we sometimes have integers like 0, 1, 2, 3, 4, 5, there is no order implied between the class labels. So for class labels, we can't say 0 is smaller than 1 and smaller than label 2 and so forth, there is really no order in the class labels. So for class labels like categorical data that is nominal, that is not ordinal, we can use the label encoder. So the label encoder, one thing I forgot to mention previously is that for the transformer API, there's a fit and a transform method. However, there is also one way you can do that in one step, and that is calling fit transform. So calling fit transform is the same as calling fit on, let's say on X, calling fit on X, and then immediately afterwards calling transform. So fit transform is just a combination of fitting and transforming in one step. So here, that is what I'm doing. I'm fitting and transforming the class label column. So fitting will just take a look at what values are present in this column, and then it will create its own dictionary where the order doesn't matter. For example, it may do that alphabetically, where class 1 will be mapped to 0 and class 2 will be mapped to 1, just alphabetically, and then it will memorize this mapping. This happens when we call fit, and in transform it will then transform these string labels to integer labels here. And the label encoder is just fine for working with nominal data where there's no order implied. So in the previous slide we talked about the class labels as nominal categorical data, and we can use the label encoder for that, because for class labels there is no order implied when we use classifiers. However, if we encounter feature columns that are nominal, we may run into problems by just using the label encoder. So for example, consider the feature column color here. So for color, if we have green, red and blue as possible values, we can't say, for example, that red is greater than green and blue is greater than red. Of course, there may be applications of that if there are certain rankings that depend on colors of uniforms or something like that. But in a general case, I would say colors, there's no order. We can't say like one color is better than the other, or bigger, better, something like that than the other. So we have now a feature column where we don't have an order implied. If we would use the label encoder, it may alphabetically assign integer values. For example, it may choose the 0 for blue, the 1 for green, and the 2 for red. So we would have something like blue, green, and red. And most machine learning classifiers would then infer an order here, because if you think back of the k-nearest neighbor classifier, it's a distance metric, right? So if we would have a feature that is 0 and a feature that is 2, this distance would be bigger than this distance. But why would the distance between blue and green be smaller than blue and red, for example, if there's no order in the colors? So that would be a problem. It would be kind of misleading to the machine learning classifier if we would imply an order even though there is none. So one way of avoiding that problem of assigning an order where there is none is using an encoding scheme called one-hot encoding. So one-hot encoding works as follows. It will create a new feature column for each possible value in the nominal feature column. So if we have the color here, there are 3 distinct values, so it will create 3 new feature columns. So we have blue, green and red now as a separate feature column, and then it will use the values 0s and 1s to assign whether the color is present or not. So for example, in the first training example we have the color green, so it will assign a 1 here and a 0 to blue and a 0 to red. For, let's say, the second one here for red, this is this one here, it would then assign a 1 to red and a 0 here and a 0 here. And then lastly for the blue one is 1 here, right? And then 0 and 0 for these two. So when we are using the getDummies method, like on the previous slide, by default it would create one feature column for each categorical value in the nominal categorical feature column. However, this creates some redundancy, right? Because if I know that the color is not blue and it is green, I know that it can't be red, right? Or similarly, if I know it's not blue and not green, then it must be red. So in that way, one column is redundant, so we can drop one column here. For example, we can drop this column and we would retain the same information, because based on the information of these two columns, we can infer the other column. So what we can do then is we can define drop first, or there's also drop last, I think. So you can also say drop last, it doesn't really matter, but we can drop one of these feature columns. So here, this is the same as above without the blue column, because it's, like I said, redundant to include blue here. Some machine learning classifiers would also run into problems if we don't drop the columns. For example, if we would use a logistic regression classifier without constraints, then we would have a problem, because we would have a perfect correlation between features, and then we would have a singular matrix and run into problems with optimization procedure and stuff like that. However, in this class, the classifiers we use, for example, k-nearest neighbors, decision trees and stuff like that, they don't have a problem with including an additional column, so this one would be just fine. However, if you think about it that way, it would just unnecessarily make the computation more expensive. If you think of k-nearest neighbors, it would just add another dimension to the distance computation. So in that way, it doesn't hurt to drop one feature column, right? Now we may also encounter a scenario where we have missing data, which is another problem. So there's also the missing data problem. For example, consider this very simple toy data set where I have two nans here. And nan, by the way, it stands for not a number. And data may be missing for many different reasons, so it's usually hard to tell what's going on if we don't have further information about how the data was collected. So it could be missing, for example, because the measurement was not obtained, or there was a mistake in the measurement, or there could be other reasons why this is not available. So that makes it usually very hard to deal with missing data compared to other data transformations. Yeah, so here are some naive ways of dealing with missing data. So if we have a very large data set where for some training examples, some measurements are missing or corrupted, and if there are millions of data points and only issues randomly occur with some of them, then we can maybe just drop these rows, because that would be solving our problem if there's no systematic issue with missing data. For example, if we have some minority class and always for this one class the data is missing, that would be of course unfortunate if we would remove it, because then the classifier would never see data like that, and then if it encounters data from this class in real life, then weird things might happen. However, assuming data is just corrupted for a small number of instances because there was some data corruption or data loss going on, then we can maybe just remove those training rows. So imagine we have a million training instances, and for two of them we have some nans here, some missing values, so why not just removing those? So we can do that using the drop NA method in pandas. So we specify the axis here as 0, so over the rows. So if there's a missing data point, it would just remove the rows. And similarly, if we have millions of features, and for some of the features missing values occur. So let's say we have a very high resolution image, like thousands of pixels or millions of pixels, and for some reason the camera has an issue in one position, so there's 1 or 2 pixel values that are corrupted. If you have a large image, 1 or 2 pixel values usually don't matter that much, so in that case we can maybe just remove the whole column in this case. So we can do that also using pandas, the drop NA method in pandas. So here we specify x is 1, so it will drop the corresponding columns. Depending on the application, and if we maybe don't want to remove data, there's also a way we can impute missing data. Of course, this is always also be taken with a grain of salt. You may introduce more harm than doing any good by keeping these data points, so it has to be decided on a case-by-case basis. However, just mentioning that things like that exist, you can, for example, impute the missing data. You can say this is just the average of over all the other feature values. So you can, from Scikit-learn, use this transformer method called simple imputer, and it will then impute the missing values that we can specify. For example, in this case, the missing values are nans, and then we can say which strategy, like the mean or median and stuff like that. So in that way it will impute these missing data points. Another technique I can spontaneously think of is just predicting the missing values. For example, you can consider this as a supervised learning problem. So what you could do is, for example, you could regard the column with a missing feature as your label column, your targets, and then you can use, let's say, all the rows for which you don't have missing data. So you would use these. Oh, let me do this differently. So this one and this one, if you combine them, this would be your training data. Of course, you would have in real life many, many more rows. So let's say this is your training data, and then you can fit a regression model on this training data, together, of course, with these labels here during training. And then after training, you have a model. And then you can use that model, given these features here, to predict this target value, right? So you can also train models to predict the target values. That would be another approach of dealing with that. It's probably a better way than just doing the average. Oh yeah, I see that is actually it for this video. It was already pretty long. So in the next video, we are going to take a look at Scikit-learn pipelines, which combines multiple aspects that we talked about. So Scikit-learn pipelines let us connect transformers, like data scaling methods and transformation methods, with the classifier and stuff like that. So Scikit-learn pipelines are super useful in practice, and that is something we will be talking about in the next video.